まだ試してなかったね。Let's continue the discussion of previous video. So we proved in previous video that each seminorm in a vector space corresponds to a corresponds to a Minkowski functional with respect to a set that is convex, balanced, and absorbing. And in this section, in this video, we'll prove that. So it's written here. We'll prove that if we are given a separating family of seminorms, we can actually construct a topology from it. And we will see later that this topology will be compatible with the topology that is given on the space. So theorem 1.37, not 17, 3, 1.37. So that P be a separating family of seminorm. Then we consider the neighborhoods VPM, which is defined as a point that has a seminorm smaller than 1 over n. Then we denote this collection B by finite intersections of these neighborhoods. And from these, we can construct a topology. So this will form a convex, balanced local base. For a topology for a tau. And we'll construct this topology in the proof. And together with this topology, the space will become a locally convex space. Locally convex space, satisfying following two conditions. First, each of the seminorms are continuous, is conti in this topology. And second, the boundedness in this topology is equivalent to the boundedness in, let's write a P boundedness. So for every P. So if it is bounded under every seminorm, it will be bounded under this topology, and these two will be equivalent. So let's start by constructing this topology. So we let the topology be constructed or by generated by this collection. Be the topology generated by this local base B, which, as defined above, is the finite intersection of a neighborhood VPNs. And this will be equal to, if we written out explicitly, it will be union of V, P, I, and I. I shouldn't write that. I should write VI. And each VI will be a finite intersection. And each VI will be intersections of finally many neighborhoods, VPN. Let's write J, P alpha J, N alpha J. Okay. So by this definition, we can easily check that this is actually topology. We'll admit it, and because every neighborhood is convex and balanced, so this will make this into a balanced, makes it into a locally convex topology with a locally convex balanced neighborhood. Local base. So these are just follows from the construction we have. So now we want to prove that this topology is actually a vector topology, which, as a reminder, it means that every point is closed. So we will only prove that 0 is closed. And second, the addition and scalar multiplication are continuous in this topology. So for the first one, it's sufficient to prove that 0 is closed. So for every x in the space, such that we can find a p such that, so this is because p is separating. So we can find a seminorm such that p of x is not 0. So we just choose mpx larger than 1, then x will not be contained in this neighborhood VPN, which implies that 0 is not inside x minus VPN. And let's call this Vx. So for every x in the space, we can find this neighborhood, right? Then we just intersect all these together. So for every x that is not 0. And because every of these, the complement. So here, because it does not contain 0, so its complement will be a closed set that contains 0 and closed. So if we intersect all these together, we know that 0 is inside that. And by the definition of a closure of 0, we know that this will contain the closure of 0. But already, this set is exactly equal to 0. So we prove that closure of 0 is equal to 0, which is that this point is closed. Okay. And the second part, we want to prove that addition and scalar multiplication are continuous, so that U be a neighborhood of 0. Then by the definition of a topology, we can find a neighborhood. That's right, P1 and 1 intersect all the way up to VPM, NM. And this will be inside the neighborhood. Then we can just choose V equals half of these. So 2 and 1, and all the way up to VPM to NM. Then obviously, V plus V will be inside U. So this proves that addition is continuous. So obviously, PI's are some seminorms, and ni's are some positive integers. Okay, next we want to prove that scalar multiplication is continuous. So that x be a vector, alpha be a scalar, and we want to find delta in a neighborhood such that also, as before, we'll just take the neighborhood of 0 as u, and we want this alpha x minus beta y be contained inside alpha x plus u for alpha minus beta smaller than delta and y inside the neighborhood of x. So what we do first, we decompose this into two components. Let's write this the other way around. Beta y alpha x. Then we put it into the difference in the vector and the difference in the scalar. So because every point is bounded, so we can find a number such that x is inside s times of v, where v is as above. And by the assumption, beta minus alpha will be bounded by delta, so the right-hand side term will be inside delta SV. So first thing we do is we choose delta to be 1 over s. And second, let's calculate the absolute value of beta. So it is smaller than alpha plus the absolute value of alpha minus beta, which is equal to alpha plus delta. Then by the choice here, our delta is 1 over s. So we want this to be alpha s plus 1 over s. So if we choose w to be, say, t times of v, then we look at this element, beta times y minus x. This will be inside alpha s plus 1 over s times tv. So what we can choose for t is simply choose it to be the reciprocal, the inverse of this number, right? So t be alpha s plus 1 over s. Then we're done. So what we have now is that beta y minus alpha x equals beta y minus x plus beta minus alpha x, which by the above argument, both are inside the neighborhood v, which are inside u. So this proves that the scalar multiplication is continuous. So this topology tau is a invariant vector topology. I think I forgot to mention that. Oh yeah, I didn't mention that. So actually we need these to be the union of translations of the neighborhoods. So this will make this topology into a invariant topology. So okay, so this proves that the topology we just construct is a vector topology, and it also is locally convex. So next thing we need to prove the two properties that we want. So first one, it says that every seminorm in this family is continuous in the topology. And this is almost trivial. So by the definition, So remember that this is a function from x to real number, positive real number. So we just look for every r a neighborhood such that the image of these neighborhoods is inside the ball R. And this is very easy, right? We just choose the n such that it's big enough. This will do the job. So we choose one for n that 1 over n is smaller than r. This is done. So the continuity of the Seminorms is very easy. And next, we want to prove that the boundedness in topology is equivalent to the boundedness in seminorms for every seminorm in the family. And it is also not hard. For the first part, so this direction, so if a set E is bounded in the topology, and we choose the neighborhood of VP1, and P is some seminorm in the family. And by the definition of boundedness, there exists a scalar such that E is contained in T times VP1. And this already implies that it is also bounded in the norm, right? So Px will be smaller than T for every x inside E. On the other hand, if E is bounded in the seminorms, which means that for every seminorm in the family, P of x is bounded by some positive number depending on the seminorm for every x in the set. Now, because as above, given a neighborhood of 0, we want to find a scalar such that it can contain the set E, right? So what we do, as above, right here, we can find a finite intersection of the neighborhoods VPN. So we just denote it as above. So we can just write it as V equals VP1 N1 blah blah blah, which is contained in U. Now what we do is, because for every norm, every seminorm, we have an upper bound, right? Mi for every I and x in the set. Then we choose an integer n such that it is larger than every mi for every I. This gives mi is smaller than ni over n. Then by this condition here, we see that x over n is smaller than 1 over n I. Is that correct? Oh, this was the other way around. So ni should be at the bottom, which means that x and are inside VPI and I, which means that x is inside n times VPI and I. So E is contained in n times V, which means that it is bounded in the topology as well. So this finishes the proof. So there are a few things that we want to talk about. That's the relation with previous results. So first one, let's talk about why we need to take the finite intersection for this topology. So remark A. So remember that we take this collection to be finite intersection of the neighborhoods VPN. If we does not do that, this will not be a local base. So let's give an example. For example, if we are in R2 and we give a seminorm of P1, P2, where P1 of X is just absolute value of X1, and P2 similarly. Then obviously these two seminorms already separates every point. But the neighborhoods VPN looks as follows. So for the VP1, so that's right, draw them separately. So VP1 looks like a horizontal strip, and VP2N looks like horizontal strips. And obviously, these does not form a local base, right? Because we can find like a horizontal set like these, and this does not contain any of the strips, so this will not form a local base. But one obvious thing is that if we intersect all these together, so if we collect all the set VP1N1 intersect VP2N2, this will form a local base. So this will form a local base. It's a local base, as the topology of R2 is generated by open rectangles. So obviously this is true. But as you can see, this is actually another seminorm. So this is actually another seminorm, which is maximum of, maybe there's some constant here, that's right, alpha P1 and beta P2. And you can check that every neighborhood can be written as this form, that is a VPN of some new seminorm. So we see that maybe we need some property that is close under this maximum operator. So in exercise 8, it just tells you to prove that if we have a family of seminorms, first is separate points as before, and second, P is closed under this maximum operator. Then this collection VPN does form a local base. So one thing you need to check first is that maximum of two seminorm is actually again a seminorm. And second is that if we have a family that only satisfies the first one, but not the second one, does not satisfy 2, then the induced collection of the neighborhoods VPN is called a subbase of topology. So making the finite intersection of the member of subbase, then we can make it into a local base. So this is the first remark. And second, as we mentioned before, if we already have a topology, so if X already have a topology that is locally convex, such that it has a countable local base, Okay, let's talk about the local base later. So from this topology, as we've seen before, the local base will induce a family P of seminorms where we are members of the local base. And this family of seminorms will separate the points, and this will again induce a topology that's called a tau 1, okay? And a natural question arises is that are these the same, or is one bigger than the other? And the answer is that they are actually the same. So to see this, we first notice that every seminorm in this family is actually continuous in tau. It's continuous in tau. So actually, they contains all these neighborhoods. So this already shows that T1 is smaller than tau 1 is smaller than tau. So on the other hand, if we are given a neighborhood in the original topology, then we just let the seminorm to be Minkowski functional of this set, and we see that W will just be mu W of X smaller than 1, as we've proven before, because remember that this will be chosen to be a convex balanced neighborhood. And this will just be V mu W1. So again, this proves that tau is inside tau 1. So they are the same. And the third remark we have is that if we have a local base, so if this topological vector space has a countable local base, or let's start with the countable family of seminorm, has a countable separating family of seminorm. Then, as we see before, this will induce a countable local base, right? So this will induce a countable local base. And from this countable local base, from the previous theorem we know that we can then construct a metric. It's metrizable. And now what we want to do is we want to construct a metric directly from these seminorms. So this is actually invariant. So what we do is we define the metric to be dxy being maximum of one plus pi, where ci is a sequence of real number that converges to 0. It's decreasing or non-decreasing. Both will do the job. But we might as well just choose a decreasing one. So now we want to do that. First, it's easy to check that it's easy to check that this is a metric. And we want to do that the topology generated by these balls is equivalent to the topology that we have. So that's right at tau p. And so it will be tau d. Okay. So first, let's look at the balls. So BR by definition will be dx0 smaller than r, where r is just some random positive number. Now, because of the definition of a metric, we can see that CIPI over 1 plus PI is actually smaller or equal to CI. So if this CI itself is smaller than R, so if this holds, then this will imply that it is automatically true for every x. So every x in x. So we only need to look at the parts that CI is larger or equal to R. So that n be a natural number such that CI is larger than R for I larger than n, larger or equal to n. Then some quick calculation will show that. So we want this CPI smaller than R. And this will become PI smaller than CI minus R. Okay, so this implies that this ball is actually a finite intersection. And the intersection looks like PIX smaller than R over CI minus R. And I is smaller than equal than R. And I have this the opposite way around. So obviously this will be in the topology of the seminorm. So this is tau p, right? And because all these are convex, this will imply that BRs are convex and balanced. On the other hand, so if we are given a neighborhood, of the topology coming from seminorm, as before, we know that W will contain a neighborhood of the form VP1N1 all the way up to VPNM. And next, what we do is that we choose R such that it is smaller than 1/2 of the minimum of C1 over N1 all the way up to Cm over Nm. And now, by the definition, we want this to hold. So CIPI over 1 plus PI, so R. If this holds, the point would be inside the ball. Next, by the choice of the R, so we have CI over 2NI. So let's see if this will hold or not. So the CI's can cancel out. We have 2nipi smaller than 1 plus pi, which is pi smaller than 2ni minus 1. Yep, because ni's are integers, so ni's are. Because every ni is a positive integer, we can calculate that ni is larger than or equal to 1. Then we add ni's to both sides. We have 2ni. And we minus 1. So we've got a denominator of this fraction here. So this is larger than or equal to ni. And this implies that 1 over 2ni minus 1 is smaller than or equal to 1 over ni. So this whole expression is smaller than or equal to ni. And this implies that if we choose R as above, BR will contain BR will be contained in the neighborhood V, which is contained in U or W. Okay, W. So this proves that tau D is inside tau P. So they are actually the same. So they are the same topology. So now finally we want to prove one of the main results of this chapter, which is the last one. So 1.39, which is I think C of 1.9, that a topological vector space is normable if and only if there exists a convex bounded neighborhood of 0. And the proof is not hard at all. So proof, this direction is almost trivial. So we just take be a normal uniball in the norm. And this will be a convex bounded neighborhood of 0, which is obviously open. On the other hand, if we have a convex bounded balanced neighborhood of 0, then we just define a norm at any point x to be the Minkowski functional of x with respect to v for every x in the space. Then obviously this is a seminorm, so we only need to check that the subspace is trivial. And the subspace is trivial because every subspace that is not trivial is unbounded, which we proved before. So the null space of this functional must be trivial as V is bounded. So this means that it is a norm. So this is a norm. Finally, we need to check that the topology are the same, right? So we just look at the balls. So the balls BR is a set such that the norm is smaller than R. Then by definition, or by the theorem we proved before, we know that This set is actually just V itself. So because V is balanced, convex, and open. So this proves that they have the same neighborhood. And because R is real number, positive real number, forms a local base. The topology is the same. The topologies are the same. So this proves the main result. And next we'll talk about quotient spaces, and finally we'll talk about some important examples. Then this chapter will be over.